This week we are on to right triangles. These things are so neat. Not only do we have the familiar Pythagorean theorem, we also have cool things like special right triangles and eventually some trigonometry. First up, special right triangles. Special right triangles are special because they have side lengths that are easy to find. Now the two most important are the 45-45-90 triangle and the 30-60-90 triangle. What do those numbers mean? You might have guessed, those are the angle measures. So the 45-45-90 triangle has two angles, which are 45 degrees, and then one that is 90. And we can relate those side lengths in a 45-45-90 by 1 to 1 to root 2, as we see in this diagram here. For example, if we were given this triangle here with the two blue angles marked as equivalent, we could determine that those angles have to be 45 degrees, and then therefore we have a 45-45-90 triangle, which tells us that these side lengths follow the ratio 1 to 1 to root 2. Comparing with the side lengths in this triangle, those fit into the ratio 2 to x to y. These ratios have to be equal because it is a 45-45-90 triangle. Therefore, we can pull out proportions to solve for these side lengths. So this tells us that x equals 2, and then likewise, we set a proportion to solve for y equals 2 root 2. So the standard ratio for a 45-45-90 triangle is 1 to 1 to root 2, and this triangle follows 2 to 2 to 2 root 2, same proportions. If you're confused by using these proportions to solve for the side lengths, I recommend you watch our video on proportions here. Next up is the 30-60-90 triangle. As you might have guessed, these triangles have angles of 30 degrees, 60 degrees, and 90 degrees. Their side lengths follow the ratio 1 to root 3 to 2. So let's see a more complicated example of how we could apply this. An equilateral triangle is inscribed inside of a circle with radius 4. What is the side length of the inscribed equilateral triangle? Let's start with a diagram, and then fill in whatever it is that we know about that diagram. First off, because it is an equilateral triangle, every angle has to be 60 degrees. This is true for any equilateral triangle. Next up, we are given that the radius of the circle is 4, so we draw that in as well. Next up, we see that the angle we have made by drawing in that radius is indeed 30 degrees, which we know because it splits the angle in two by going straight through the middle. So now we have, very interestingly, a 30-60-90 triangle, which one side length, the hypotenuse, is the distance that we want. But we don't know any of the other sides because even though it might look like it, we don't know the side down the middle. So how can we build another 30-60-90 triangle that we do know something about? Well, if we look at this smaller 30-60-90 triangle that has a hypotenuse of 4, the given radius, now we can pull out this 30-60-90 triangle and use it to eventually find the distance that we want. At this point, you might be thinking, how the heck did he know to do that? Well, it can be tricky, but with these types of problems, you really just need to get comfortable walking in the dark, filling in your diagram with whatever you know, and eventually the answer will pop out one way or another. So let's keep going and get to a final answer. Because this is a 30-60-90 triangle, we know that the side lengths follow the ratio 1 to root 3 to 2. Filling in the side lengths in this triangle, we can then use those ratios to set up a proportion to solve for the unknown side length x, as we've written here. Doing so gives us x equals 2 root 3. We're not quite done. Now we have to look back to our diagram and see that the distance we're actually looking for is twice this value that we just found, 2x, just by looking at our diagram. So our final answer is 4 root 3, and we're done. Hooray! We finished with the most important special right triangles, 45-45-90 and 30-60-90. Now the last one is not as crucial to know, but can be very helpful. It is called a 3-4-5 triangle. It is called that because the side lengths follow the ratio 3 to 4 to 5. Unlike 30-60-90 and 45-45-90, we don't know anything useful about their angles, but those side lengths make them very useful. As a quick and easy example, say we were given this triangle here with side lengths 9, 12, and x. Based on the 9 and the 12, which will look a lot like 3 and 4 each times 3, we can identify that this is a 3-4-5 right triangle. Therefore, we can guess what x would be, and not just guess, but know for sure. Because it follows the ratio 3-4-5 and then times 3, then x is just the 5 times 3, 15. And that's as simple as that. We don't have to use the Pythagorean theorem, which would take much longer. Lastly, for some basic trigonometry, including our simple trig functions, sine, cosine, and tangent, and then lastly, how to measure angles in radians instead of degrees. Luckily, the SAT does not test trigonometry too often, so don't expect to see this very frequently. Trig functions are easy to memorize with SOHCAHTOA. SOH, S-O-H, stands for sine is opposite over hypotenuse, meaning sine of x is equal to the ratio of the opposite side length over the hypotenuse length. Recall that hypotenuse is the side opposite the right angle and is the longest side. Ka, or C-A-H, tells us cosine is adjacent over hypotenuse. Lastly, TOA, T-O-A, tells us tangent is opposite over adjacent. Last up is radians. These are important to know to understand, as well as how to convert between degrees and radians. Luckily, this is pretty straightforward. A circle has 360 degrees going all the way around, and in radians, that is the same as 2 pi. So to convert from degrees to radians, then we would just need to multiply by radians over degrees, which is 2 pi over 360. The other way around, going from radians to degrees, would just be the opposite, 360 degrees over 2 pi radians. Now we just simplify those factors, and now we can do some examples. So let's take 180 degrees and convert that into radians. Well, to go from degrees to radians, we need to multiply by, as we found, pi over 180. Simply evaluating gives pi. So 180 degrees is equal to pi in radians. Let's do one more example going the other way. So let's say pi over 4 radians equals how many degrees? So we need to multiply by 180 over pi, like we found earlier. Doing so is going to give us, evaluating, 180 over 4 after the pi's cancel, and then finally 45. So pi over 4 is equal to 45 degrees. And that's all for this week. Study up, because there's a lot that we looked at today. 30, 60, 90 triangles, 45, 45, 90 triangles, 3, 4, 5 triangles, and then our basic trigonometry, SOHCAHTOA, as well as radians. After we cover circles next week, you will be ready to tackle any geometry problem you see on the test. Hope you liked the video. If you want to hear more and see what else we're up to, hit like and subscribe, and see a new video coming out from Point Avenue every week. If you want to talk to us, hear more about what we're doing, or have any questions, email us at contact@pointavenue.com. Bye!